Welcome to the, I do not know, let me have a look at. This is the Lebesgue integral continued. Yesterday, in the last session, we proved monotone convergence theorem and gave some applications. Okay, and it's one of the most beautiful and also an important tool in the theory of integration. Okay, today we will also give a third application and plus applications of such applications. Okay, secondary level applications. All right, okay, let's get started. Yeah, it is measure theory 21st session and 4th session on Lebesgue integral and monotone convergence theorem applications continued. Okay, so now we look at, I think I gave two applications in the last session. This is application number 3. What is that? So let, as usual, X be mu a measure space and assume fn's are non-negative measurable functions. Right? Then, as we know, integral fn makes sense. Okay? It is defined and it makes sense. Now let f equal to summation fn. So what is the meaning of this object? This is for each x in x, we define fx by the sum of the infinite series fnx. And notice that fnx are non-negative, therefore the partial sums will be an increasing sequence. So its LUB or supremum exists in 0 infinity. Okay, it may exist as infinity also. So this is always defined. It belongs to 0 infinity. Therefore fx is defined. Okay. So the sum makes sense is what one must observe. So now what we want to claim or we want to prove is that integral of, look at summation fn d mu over x, this is same as integral of f. Okay, that is the summation. Okay, the summation and integral can be interchanged. It's a loose way of saying. Okay, so understand this statement. Proof is very easy. So we want to deduce this from monotone convergence theorem. Okay. So that means I have to look at an increasing sequence of non-negative measurable functions. Where will I find it? Obvious. Let it Gn, instead of Sn, let me write as Gn. Gn equal to Fk, k equal to 1 to n. Okay. Then the Gn's are measurable and Gn increases. Okay. So where does it increase to? Gn increases to f, where f is summation fn, 1 to infinity. Okay, that's because Gn of x will be equal to the partial sum of this series, right? The partial sums of summation fn of x or fk of x k equal to 1 to infinity. Right. Okay, this increases. Therefore, by monotone convergence theorem, integral of Gn increases to integral of g, integral of f. That is integral of summation fn. Right? But what is integral of Gn? Remember, Gn is by definition fk, k equal to 1 to n, and you had already seen integration is additive for non-negative function. Integral f g d mu is integral f d mu plus integral g d mu. F and g are non-negative measurable. Okay. As a consequence of MCT, we already proved this. Therefore, by induction, it also follows. Therefore, integral of Gn is therefore equal to integral of n. k equal to 1 to n of integral of fk, right? Therefore, what we mean is integral of k equal to 1 to n summation k equal to 1 to n of integral of k increases to integral of f. But notice that by definition, this increases. The limit is k equal to 1 to infinity of integral of k, right? So I'm not writing increases. This increases to this below increases to this. But the limit being unique, we conclude these two are equal. Okay. So pause, review, proceed. Okay. So this is one of the typical uses of monotone convergence theorem, and application of this application. Three is the following. Let us stick to a very specific case of n, p of n, and where mu is a counting measure. So if f is from n to 0 infinity, we know that integral f d mu over n is nothing other than the sum of the infinite series we had already seen, right? So suppose I have sequence fm from n to 0 infinity, right? So let me call fm whose value at n to be the real number mn. When I say real number, extended real number. Okay, right? Now there are two things. Therefore, I can talk about integral of fm. Okay, sorry, integral of fm d mu over n. But this is nothing other than fm at n equal to 1 to infinity. This is summation n equal to 1 to infinity of am. Is that clear? Right. The next thing I can talk about is f, which is summation fn. Okay. Therefore, f at n here is summation fm at n, and here what is running? M equal to 1 to infinity. Right. So this is my fn. Therefore, what is the integral of f d mu over n? This again by definition is summation f of n equal to 1 to infinity, but this is summation n equal to 1 to infinity of summation m equal to 1 to infinity of fmn, which is summation m equal to 1 to infinity of amn. So am. Yeah. Now, do you see what we have got? So what we have got now? So we have, so the integral, so let us again make it clear, f d mu therefore equal to n equal to 1 to infinity or m equal to 1 to infinity of amn. Okay. On the other hand, summation of fmm, okay, that is here, this summation fm and m equal to 1 to infinity was summation m equal to 1 to infinity of, this is am n, that is here n equal to 1 to infinity. By the last corollary, these are equal, that means these are equal. So what does it mean? This means if amn is a double sequence, when I say double sequence, you see, it's a function from n cross n to 0 infinity. Okay. Then there are two ways of adding this, that is amn, you add it with respect to n, then add it with respect to m, or you add with respect to m first and then n first, they are the same. That's what we have proved. Though we can interchange the order of the summation. Remember, a particular case of this we already used. If it's a finite thing, that is f1 to fm only exists. Okay, we used it in one of the earlier things when we discussed about mu s, where s is simple non-negative. Then this is a countable additivity. We used this in the finite case. It's easy, but in infinite case it needs a proof. Okay, that's what you are given. Please spend some time, pause, review, proceed. Okay, see, this is how I think. Just because I proved, that's not enough. I also see that something is special case we had already seen, in which context. So at such places, what I do is I stop, pause, and quickly review the earlier proof also, so that most of the things, the way we learn multiplication table, we keep on using it, revising it. Then things like 7 times 8 and 3 times k 9, everything comes immediately. You don't have to repeat the table. All right, the same way you keep on reviewing. Whenever there is an occasion, stop and try to see how you did earlier. Yeah, let's proceed. It's time that I already said monotone convergence theorem is actually about increasing sequence. About increasing sequence. Yeah, and of non-negative measurable functions. Right? So when we try to see, suppose fn's are non-negative again, but now fn's are decreasing. That means fn of x is less than or equal to fn minus 1 of x. That is fn plus 1 of x is less than or equal to fn of x for all n and for all x. Okay. Then can you do the same thing? Then integral fn, okay, will be greater than or equal to integral fn plus 1. Therefore, this integral fn as a sequence, this is a decreasing sequence. Right? And this, since this decreases, fn of x decreases to some number of x, again in 0 infinity. Right? Therefore, I can wonder whether integral fn decreases to integral f. Then it will be actual monotone convergence theorem. Okay? This may not happen. Okay? I will tell you the best way to learn. These are the things which are never discussed in a classroom or textbook. The best way to see this, review the proof of MCT. See, whatever I did was something like, okay, the crucial thing was we looked at mu of s n or whatever it is, mu of s is a measure. And therefore, whenever en increase to e, we know that mu of en increase to mu of e. This is true for any measure. But we already have seen example, if bn decreases to b, mu of bn decreases to mu of b may be false. It is true only under the extra assumption there is at least one n such that mu of bn is finite. Only extra assumption is needed. So we are not doing anything here. Right? So, and what are the example to do that? Remember my bn with respect to the r and m, my bn I chose was something like n to infinity. Okay, then bn decreases to empty set. This was a contradiction. So this gives an example also. Okay, so MCT is false in general for decreasing sequence. Okay, the example is, let us look at fn equal to indicator function of n infinity. Right? Then, okay, this is my n. This is my n plus 1. Alright. Therefore, if my x is less than or equal to n, fn of x, let's say I write strictly less than n, fn of x will be 1 equal to fn plus 1 of x also. But if my x is between n is less than or equal to x less than n plus 1, my fn of x will be 1, but fn plus 1 of x will be 0. Right? And if my x is greater than or equal to n plus 1, then fn of x will be same as fn plus 1 of x. Right? Therefore, we see that fn decreases. Fn, the sequence fn decreases, not fn as a function. Okay? The sequence fn decreases. Right? But what is integral of fn? Since it is integral of characteristic function with respect to dm over r, characteristic function of n infinity, this is a measure of this interval is infinity. Right? And fn decreases to since 0. Why? What does it mean? See, fn of x, right? Look at that. Give me any x, given any x in R by Archimedean property, there exists n, maybe capital N, so that yeah, x is less than n. Okay, this is my x, this is my n. Therefore, for any n greater than or equal to n, what is fn of x? It is integrated function of n infinity of x, which is 0. Right? Therefore, for all x in R, fn x is eventually 0 sequence. Right? Therefore, fn x converges to 0 for all x. Right? Therefore, that is my limit. But integral of f over 0 over R is 0. Right? Therefore, integral fn does not decrease to integral f. This is false. Not true. Okay? A slightly better example is slightly modify. Suppose I define fn of x the same way, except I multiply by 1 by n, integrated function of n infinity. Yeah. Now fn converges uniformly and it actually decreases uniformly to 0. Okay, but still, but integral fn dm is 1 by n times infinity, therefore it's infinity, but integral f is 0, so still it's not true. This I leave it as an easy exercise. It decreases, we had already seen essentially. Okay, the only thing is it's uniform, that's also easy. Okay, please do that. Okay, P R. So please note that this is a kind of trap. Many students, okay, they believe just because we proved for increasing, decreasing, it will also be true. Okay, and when I ask for how about MCT for decreasing sequence, they will say yes. Okay, that's not true. Yeah, please understand that. Now we will give one more telling example of monotone convergence theorem. It's not an application. Of course, I have to apply MCT, but then you will see the marked difference between the Lebesgue integral and Riemann integral. Okay, let us look at it. So It's an example. Let's look at the set zeros and rationals. Call this set as E. Okay. Then this is countable. Okay. Let E be the set of rational numbers 0, 1 be enumerated. What does it mean by enumerated? You know, I hope, right? Set up your bijection F from natural number to E, and F of n you call it Rn. This is a bijection. Then this Rn is called enumeration. No, this is the word, okay, jargon which is used, right? Now let En be equal to Rk 1 less than equal to k less than equal to n. That is R1 to Rn, right? Now let my Fn be equal to the indicator function of En, right? Then you can see Fn increases. Yeah, do you see that? To F. What is F? F is nothing as an indicator function of V. Why? Because Fn of x, you have to look at, so if x is in one of the Rn, suppose x equal to Rn, let us say Rn, okay, then Fk of x will be 1 if k is greater than equal to n, because if k is greater than equal to n, my Rn belong to Ek. Therefore, Fk of x, the indicator function, that will be taking value 1, right? Therefore, what I say is if x belong to E, then Fn of x is eventually 1. Therefore, Fn of x converges to 1 if x is in E. Suppose x is not in E, then x is not in En, and hence Fn of x is always 0 for all n, right? Therefore, Fn of x converges to 0, right? Therefore, Fn converges to the indicator function of E. This is the so-called Dirichlet function. But notice that we know that Fn increases to the indicator function, the Dirichlet function, and each Fn is measurable. Why? Okay, what is integral of Fn? It is integral of characteristic function of En with respect to m. Okay, but that's a finite set and it's a countable set. Therefore, it's measure of En which is 0. Therefore, integral each Fn, integral Fn exists in Lebesgue sense. Right? And integral Fn according to MCT, it converges to integral of F, which is also 0. That we had already seen. This is already seen when we talked about integral of functions S from S plus. Okay, we had already seen this because this is a characteristic function of this set, measurable set. Okay, but important thing is each Fn is a Riemann integrable, because you have, say, R1, R2, Rn, okay, and right, so I can always break into this. This is going to be integral here, it's going to be integral here, and so on. Okay, or if you want to say each Fn is 0 except at Rk 1 less than equal to k less than equal to n. Okay, therefore the finite number of discontinuous Fn has only finite number of therefore Fn is Riemann integrable. And again integral Fn 0 to 1 Fn of x dx is 0. These are all easy. I don't want to spend time on that. Okay, each Fn. But and also Fn increases to F, but F is not even Riemann integral. So there is no question of integral f and whether it can increases to integral f or not, because this does not make sense. Integral, okay, 0 to 1, 0 to 1, f of x dx, fn of x dx, this fellow does not make sense. Okay, P or did you like that example? Yeah. See, this is how, small things, the more and more we work with that, the more confident we become. Right? Okay. So I think I have completed more or less the standard results concerning monotone convergence theorem. Okay. Usually in the typical classroom, monotone convergence theorem, immediately they will prove as a corollary Pathos lemma, and next day they will prove a dominated convergence theorem. Okay. But it's good, whenever some result is done, try to look for some small exercises, examples which illustrate or where it can be applied. That is the way to master such result. It's not only the proofs. Okay, as I keep saying, the statements are more important and the typical uses of such results are more important. That is the way we can master the subject. So the next one, it goes under some Russian mathematician's name, Chebyshev, but okay, the spelling is not uniform, like almost all Russian names. Okay, depending upon one's women fancy, people spell it the anyway they want. A typical case in mind is taken off, right? Even I had used to many different ways of doing it. Okay, there is no uniqueness, so we will go to say that, but it's a very easy result. But it tells you some of the typical way how the integration is used. So, yeah, it's recorded. Okay, this is called Chebyshev. Okay, sometimes this T is missing. They will write capital C, Chebyshev. It's all okay. As I said, it's not unique. So let F be measurable and let, okay, alpha be in 0, alpha be positive, right? Then what we want to look at is, we want to look at the set E alpha where F is greater than alpha, right? I want an estimate for the measure of E alpha. This is what Chebyshev inequality. So the only thing you have to think of, what is it about? After that you can form, okay, you can prove and then formulate the result. That's what I'm going to do. Okay, I don't remember often the statement, but you will do that. You understand that? So this is something like this. So suppose I have, okay, this is a function. Okay, suppose this is my alpha. Okay, so this is. So I want an estimate for this measure. These are all constitute E alpha, right? So let us do that. So what is E alpha? E alpha is a set of points x in x so that fx is greater than alpha. All right. Okay. Now let's look at integral f. Right. So integral f over x. Okay. Let us look at f and f times indicator function of E alpha. Then f is greater than or equal to f into integrator of E alpha. Yeah. Shall I call it only E? Okay, alpha is fixed. Okay, fix alpha. Okay, so indicator function. This is clear, right? Therefore, this will be greater than or equal to integral of f over I over x. Is that clear? But this is by definition integral of f over E. Right? On E, I know fx is greater than or equal to alpha. On E, f is greater than alpha. Therefore, this by monotonicity, this is again by monotonicity, and this is again by monotonicity of the integral alpha times, right? So that is equal to, but this I know what it is. It's alpha times measure of E, mu of E, right? So what you have found is alpha times measure of E is less than or equal to integral of f over E, which in turn is less than or equal to integral of f over x. So in particular, mu of E is less than or equal to 1 by alpha times integral of f over x d mu. This is Chebyshev's inequality. Notice that if it has to be of any use, this must be finite. Then only we get something, an estimate. If this is infinite, okay, 1 by alpha times that will also be infinite, there is no result. You understand that? So, typically where we will use? Typical uses when integral of f d mu is finite. Okay, pause, review, proceed. So now you can see that we can estimate the measure of a set which is defined in terms of the behavior of the function. Okay, this is a, see, analysis always means this. I need to estimate something or the other with respect to some function. Either the set is too big, cardinality wise, or too less in terms of measure theory or topology or some such thing. This is a basic idea of analysis, right? So this one gives an idea. If f is such that integral f d mu is finite, then I have a very good estimate for mu b, right? That's it. Okay, please understand this inequality is more often used. Okay, but I don't have to really, I usually don't remember that. What I do is, as you can see, the proof is very simple. So whenever we need, we simply use that idea. We use the proof. Okay, idea of the proof rather than recall Chebyshev inequality and say that. Okay, that may be easier. It's up to you. If you have good memory, well and good, go ahead. So let us try to make use of this thing. So these are all some general, okay, how to deal with Lebesgue integral of non-negative functions so far. Because we have defined only Lebesgue integral for such functions. Right? For example, Chebyshev inequality is one such. Many are, okay? Right. Just for fun, let me say, suppose I have f from x b mu to 0 infinity is measurable and m is 0 almost everywhere with respect to mu. Okay, what does that mean? The mu, the measure of the set x in x, such that fx is not equal to 0. This is a set of measure 0. Right? Do you remember how did you define almost everywhere? The property is the set of points at which it's not true, okay, is what we are doing. Okay, right. So f is 0 almost everywhere. Then I would like to say, for example, typical examples. Let us look at again our q. Then let's look at I of q. Okay, this is 0 almost everywhere with respect to the measure. Right? We had already seen such example. In case you had forgotten, we have not used it, so I'm recalling. All right. So what do you think the integral of this must be? If this is any typical example, then you should expect it to be 0. Okay, or Gus. This was Gus. Okay. How do we prove it? So the reason why I took this example is, as I keep saying, every time go back to the definition when you are stuck somewhere. So now how did f is a non-negative measurable functions? How did I define the integral? It is the LEB of integral of simple function s, where s is a simple function such that 0 less than or equal to s less than or equal to f. You understand that? So I will make use of it. Remember, even in MCT we made use of it. Okay, always go back to the definition. So suppose for that means what? Therefore we are assuming integral of f d mu over x is positive. Okay. Now by definition there exists. Okay, what is integral of f d mu over x? This is by definition LEB of integral of s, where 0 less than or equal to s less than or equal to f, s in s plus. Right? Therefore, what does it mean? The least upper bound is positive. Therefore, there is at least one simple function s such that integral of s d mu must be positive. Because if for each s here, for each such s like this, integral of s is 0, then LEB will also be 0. That means integral of f will be 0, right? Therefore, this claim is true, right? So choose s in s plus so that integral of s d mu is positive. Now let s equal to summation ci indicator function of ai. Okay, it's a standard representation. Notice that each ci is greater than or equal to 0, right? And what is integral of s? Integral of s this by definition is summation ci mu of ai I equal to 1 to n. Right? Now we are saying this is positive. And remember, CAs are non-negative because this is a positive function and mu's are also non-negative. Right? Therefore, there exists at least one j such that Cj into mu of aj is positive. Is that clear? Yeah? Okay. That means Cj is positive and mu of aj is also positive. Correct? Therefore, for all x in aj, what do I have? F of x, since it is greater than or equal to s times s of x, that is equal to Cj. I know that fx is greater than or equal to Cj for all x in aj. Right? Now let us use monotonicity. Integral of f over x du mu, right? F is greater than or equal to f into indicator function of aj. Right? Therefore, by monotonicity, integral of f du mu is greater than or equal to integral of f I of aj d mu. That is equal to integral of aj. Okay. On this side, okay, this is greater than or equal to c, right? Therefore, c. Yeah. And this is c times cj times mu of aj, which is positive. So this is a contradiction. Oh, I'm sorry. This is not what I want. I'm sorry. I'm sorry for this. Let us look at this. This is already good enough for me. Yeah. I'm sorry. Okay, come back to this. So what we have shown is on aj, okay, we have fx is greater than or equal to cj, which is positive. Right? Therefore, Aj is contained in set of x in capital X such that fx is not equal to 0. Therefore, mu of Aj should be less than or equal to mu of this set. But that is 0, but this is positive, a contradiction. So pause, review, proceed. I'm sorry, I got slightly, lost track of it. It's an if and only statement. So I just, my mind started working on the other side. So what have you shown that? Please understand, if f is equal to 0 almost everywhere, integral of f must be 0. That is what we prove. Is that okay? Now I can ask the converse. What is the converse? Suppose f is non-negative measurable function and integral of f is 0. Can I conclude f is 0 almost everywhere? Okay, that part of the proof is what I went through towards the end. Is the statement clear? Let us do it, and then with that we will end the session, today's session. So converse is the following. F is 0 almost everywhere. Suppose false. What does that mean? That means there exists a E in B, measurable, mu of E is positive, and for all x in E, f of x is not equal to 0. In fact, f of x is positive because we are assuming non-negative. Do you understand that? If it is false, okay, then there is a set of positive measure on which f has to be non-zero. Since f is non-negative, it has to be positive, right? Therefore, for each natural number n, let me define my en to be set of x in capital X such that f of x is greater than 1 by n. Yeah? Right. This is okay? Right. Now, let us try to do that. Now, en increases to e, where e is the set x in capital X such that fx is not 0. That is same as fx is positive. Do you understand this? Right? Okay. Therefore, what we have is, let us look at f equal to I of fn, okay, f into I of en. That's less than or equal to integral f. Right? Okay. So, therefore integral of f over e, sorry, f into I of en increases to f into I of e. Is that clear? Yes? Therefore, by monotone convergence theorem, integral of f I en, okay, increases to integral of f over ie. Okay, this is the integral of f over e. Right? But that is less than or equal to integral of f over x, which is 0. But remember, okay, now since mu of e is positive, there is at least one n in n, so that mu of en is positive. Or otherwise what happens? Union en is e and each n mu of en is 0. Okay, that implies mu of b by countable subadditivity is less than or equal to mu of en. which is 0, therefore mu of is 0. That's a contradiction. Therefore, there is an n so that mu of n is positive. This is enough. Okay. Again, I am sorry, we don't need this. Therefore, integral of f over x is greater than or equal to integral of f into I of en over x, but that's integral of this is greater than or equal to 1 by n, okay, over en, right? Now this is 1 by n times mu of en, which is positive. So this is a contradiction. Do you see the last part was what was mixing with the last part? And again here also I unnecessarily got into MCT that was not needed. Okay, this is just to show I am thinking here rather than trying to recall and do something. I hope you enjoyed these things. These are the typical application of, okay, it also, all these examples teach you how to deal with Lebesgue integral. Okay, the first thing is you may have to go back to the definition of integral of a simple function and integral of non-negative function in terms of integral of simple functions and their LUB and monotone convergence theorem if I need. Okay, there is one more important thing. I do not know whether I have time, so there seems to be a little more time. Just 1 second, the power is running out. Yeah. Yeah, power is restored. Okay, so I still have about 10 minutes, so let me finish that also. I thought this will be the last one, but we still have time. I'm just aiming for an hour, 55 minutes, thereabouts. Okay. You remember when S is a non-negative simple function, we define mu of s and showed this is a measure on x, b, right? Similarly, we are going to say if f is non-negative measurable, then I can define mu of f of e to be equal to integral of f over d. Okay, we want to say mu of is a measure on x, b. So you see, we generate lot of measures. Once we have defined Lebesgue integral, we have a lot of measures. The proof is exactly similar. Okay. So let us do two things. I will just explain quickly. Okay. So what is mu of A union B if A and B are disjoint and they are measurable? Then this by definition is integral of F over A union B. Integral of F into I of A union B. But that is, since we had already seen I of A union B is I of A plus I of B in the case of disjoint measurable. Therefore, this integral of F of I of A plus I of B. But we know integration for non-negative measurable functions additive. Therefore, this integral of F I of A plus integral of F I of B. But this is by definition mu of A plus mu of B. Therefore, the first observation is mu of F is finitely additive. Right? The second observation I can actually directly do from the earlier result, but I'm just going to. Next thing is, suppose my En are in F, B, and En increase. Then I want to say mu F of En increases to mu F of B. That also follows because F of IEN increases to F of IE. So, monotone convergence theorem says integral of F IEN increases integral of F of IE. but this is mu of En, that increases mu of E, right? And in abstract measure theory, we have seen if mu is any set function from a sigma algebra to 0 infinity, which is finitely additive, and if En increases to E, implies mu of En increases to mu of E, then mu is countably additive. Therefore, mu is a measure. Therefore, mu of is a measure. Because mu of is countably additive, it also has the increasing measurable sets. A direct proof will be this. Okay, suppose En pairwise disjoint, let E equal to union En. Notice that I of E is summation I of En. Okay, is right. Therefore, integral of mu f of E is integral of f over I of E, right? But that is equal to integral of f over summation I of En. That is integral of summation f into I of En, right? But as a third application, from the third application of monotone convergence theorem, this is same as integral of f of or f into I of En, right? Do you remember integral of fn equal to summation integral fn? Okay, this is also known as Levi's theorem. Even monotone convergence theorem is sometimes called Levi's theorem. Both are equivalent anyway. So I hope you are okay, right? That means this is what mu of En, mu f of En, and this is mu of E. So we proved countable additivity. Okay, as far as I can remember, these are the basic results. Okay, please go through each one of them. There are very what you call tukadas, small pieces. Okay, so but each one of them kind of reinforces our understanding of Lebesgue measure and Lebesgue integral. Okay, please go through that. I hope you enjoy this lecture. These kind of applications should be done. There are no, okay, as I said in the executive summary of Lebesgue measure, you just have to know what are the properties. Okay, but the merit of Lebesgue integration theory is learning how to use Lebesgue integral, the monotone convergence theorem, and the definition of integral, and there are two more theorems. I will come to that. So the bulk of the thing is the so-called convergence theorems in Lebesgue theory. One is monotone. In the next session, we are going to look at Patho's lemma, and the third thing is dominated convergence theorem. These are the real kind of heart of Lebesgue integral. One has to master them. So in each one of them, I will try to think of typical good applications so that you will know how to work with Lebesgue integral. That is the aim of the course. Okay. Thank you very much. We will meet again. Stay safe. Take care.